Hello everyone, my name is Mason Duhon, and I am a senior mechanical engineering student at Lamar University. I will be telling you today about thermosyphons. Thermosyphon is a type of heat exchanger that doesn't require a pump or any other kind of external motive force to move the fluids through the evaporators, condensers, and throughout the rest of the system as well. A thermosyphon is a passively driven thermal management device that utilizes the motive forces of natural convection and conduction. These motive forces are also gravity and a usage of the densities. As the water is heated and cooled, it changes its density, which also causes it to move. So as you can see in figure 1 here, the tank is kept with hot water on top, cold water on bottom, naturally as the densities sort. So the cold water will then filter down into the collector or the evaporator and then be heated by the solar energy, which will cause the water to heat up and rise back up to the tank where it can be dispensed or returned. Now, as you can see in figure 1b, that is the same cycle, however, it is reversed. And since the evaporator is higher than the condenser, the whole system needs to have a pump. And because it needs to have a pump, it also needs a controller. As you can see, figure 1a is a thermosyphon, figure 1b is not, because it requires this pump and external energy is used to to fuel the system, so to speak. I chose a thermosyphon because I decided that a thermosyphon is the closest thing to a perpetual motion machine as possible that we can feasibly get. Of course, we're not going to achieve a perpetual motion machine. That is impossible by thermodynamics. But however, a thermosyphon does allow us to design a system to be much more energy efficient. And because it does not require a pump, it is very easily maintained, as there are no moving parts. But the downside of some of these thermosyphons are that they rely heavily on gravity and hydrostatic pressure to return cooled fluid back to the heat source, making them a little trickier to design. So another common heat exchanger that could be used instead of a thermosyphon is a heat pipe. A comparison to heat pipe and heat sinks of the thermosyphons, you will see that a heat pipe requires a wick, this area around the inner perimeter of the heat pipe. That wick transports the liquid from, that wick is essentially what what gravity does for the thermosyphon. You see, a thermosyphon, instead of using capillary action, much like this wick uses capillary action to transport the condensate to the vapor, a thermosyphon will simply use its gravity and its density and static and hydrostatic properties to propel the fluid throughout the system. The differences between a heat pipe and a thermosyphon. Now, there are very similar designs, however, they are not the same. They are both passive superconductor. They're both passive heat exchangers, both superconductors, and they are both two-phase heat exchangers. They are both vacuum-tight and pressure vessels. However, this is where the differences begin. The liquid on a heat pipe is returned by a capillary wick, as opposed to the thermosyphon that is returned by gravity. Because of that, a large amount of design for thermosyphon hinges on the fact that the evaporator is lower than the condenser. However, with a heat pipe, the orientation can be whatever you would like. And typically the length of a heat pipe is 1 foot, compared to a thermosyphon is under 1 foot, compared to a thermosyphon that is unlimited in length. Another downside of having this capillary wick is that oftentimes the capillary wick will burn out. I say burn out. It will absorb too much thermal energy that it will dry out, and this causes a state of wick dry out, of heat pipe wick dry out. So the most practical applications of thermosiphoning is whenever mold and mildew are a major concern, for example in residential areas or even some commercial buildings. As you can see, mold and mildew forms at a relative humidity of 60%, and whenever it's maintained at that 60% for extended periods of time. When a lower humidity is desired or increased air is needed, a thermosiphon is the best choice, because a thermosiphon will not use a sprayer or any other means of relative humidity control that other AC systems will use. A thermosiphon will instead most likely use the solar energy or some other sort of energy. Some homes will actually take the option of using a two-phase thermosiphoning loop that can be used for solar water heating. This is exhibited in that figure 1 from previous. Thermosiphons can also be used in internal combustion engines as radiators and other cooling devices. Thermosiphons are not perfect. They are not to be used to replace conventional equipment that is capable of doing the job correctly. They are, unless the conventional equipment is requiring external heating because the inlet is being supercooled, it will not be cost effective because you would have to pay to get the old equipment out on top of installing the new thermosiphon equipment, which isn't cheap on its own. Thermosiphons are not a miracle cure. They're not going to create this perpetual motion, as I've previously stated. Advantages of using a thermosiphon. A thermosiphon is a passive heat exchange with no moving parts. It is relatively space efficient and can reduce equipment size in some cases. Sometimes the AC system is ridiculously larger than it has to be, and sometimes a thermosiphon system will reduce it significantly. The moisture removal capacity of existing cooling equipment can be improved with thermosiphons. For solar energy, a lot of the relative humidity is eliminated solely off of the usage of solar power to heat the air. And because of this, their moisture removal capacity of existing, and because of that, the removal capacity can be improved. And you can also string a thermosiphoning system onto existing equipment as well to further improve upon that. The no cross-contamination between air streams with coil type is another huge advantage of thermosiphoning systems. One of the downsides of thermosiphons is that average efficiency of a thermosiphon ranges between 40 to 60%. They're not the most thermally efficient devices. They may require even a significant temperature difference, meaning they may require a spark to get started. It's mainly to get the condensate boiling in the evaporator to return to condenser and continue the flow. They may require a significant temperature difference to initiate that process. A condenser, and of course, as we've heard several times in this presentation, the condenser must be above the evaporator to allow the condensate to return without a pump. Here you can see a thermosiphon design for I believe this one is for a car's radiator. As you can see, the thermosyphon is designed that the water may circulate naturally because of the density difference between hot and cold water. The hot water in the jacket rises and flows into the upper tank due to the lower density compared to cold water, and also vice versa. Hot water from the upper tank will then flow towards the lower tanks, and then the fan is fitted to the drive shaft, to the crankshaft, I mean. This increases the cool down effect here and allows the cold water to further move throughout the system. To increase the rate of heat transfer, the surface area of the radiator, right here, is covered in fins. That way the air blast, it hits the most surface area possible. Automobiles and transformers use the same principle of cooling. However, since the thermal efficiency is only 40 to 60%, this is mainly for low capacity engines. And this system can also be used in CPU cooling as well, and is in fact. So in conclusion, thermosyphons can be used in a variety of applications, whether that be air conditioning in houses, offices, plants, and even water heating in houses, plants, offices, and even being a radiator for cars and CPUs. They will constantly be ever present and will be ever more present in the future. Future developments may increase the usage of thermosyphons due to their lack of external power usage, making them a lot more desirable in many industries because everyone loves to save money. Because, hey, who doesn't like money? Another major point that we talked about today is that if the project is not already installed, a thermosyphon is definitely a viable option. However, once that project gets installed and is fully functional, well, a thermosyphon might not be the best choice because you would have to pay to remove that equipment and then pay to install the new equipment. Due to the cost, a thermosyphon will not be cost effective if replacing already functional equipment. As previously stated, unless the equipment is causing an external heat source, is requiring an external heat source to provide the heat needed because the heat pipe inlet is supercooled, then a thermosyphon will definitely be the best match. Here's my references. Actually, this website here is a great one. For more information on thermosiphoning, it is top-notch. For more information, of course. And thank you all for taking the time out to listen to me, and I hope you all have a wonderful day, and go Cards!